operation and this operation, and multiplying by b squared on this side, does the equal sign hold?
Okay, so you are talking about only if you give us the wave function in a formula rather than...
Correct. In this class, I'm not going to ask you to look for what y would work. I'm going to say, does this y work? In your differential equations class, your job is they give you the differential equation, you try to find y's that fit. All I'm doing is you saying you test it. I give you this, I ask you, is it valid? You put it in here and you say, it's not obviously invalid. You're not claiming that it's valid yet. You're just claiming that it's not obviously invalid. Okay, so that's a critical question that she asks. And I want to make sure everybody understands what she asked and my solution to it, or my answer to it, okay? Good. Exploit Young's experiment. And number one, our first goal is, of course, to demonstrate that light is a wave. That's going to be our fundamental goal. But our secondary goal is to see if we can estimate the wavelength of red light. And when I'm done showing you how we're going to do this experiment today, you're going to be amazed that we can get any sort of a reasonable estimate for the wavelength of light using, among other measurement tools, a meter stick. How can you measure the wavelength of light with a meter stick? We're going to actually do it. Well, we're not going to measure, but we're going to make a reasonable estimate. Furthermore, let me explain that this Class O demonstration, class participation demonstration, will serve as a laboratory. So this laboratory will be titled Young's Experiment. And as a group, you will gather the data. And each one of you will use that same data to do the writing. So perhaps we can have somebody scribe the data on the board as you're gathering it. And then all of you will have access to the data. And you can do a lab write-up. There are a couple of important points. One of which is, in a class this size, it becomes a little dangerous. There's always someone who just sits and waits and does something else until the data's on the board, copies it down, and leaves. Okay, fine, but could you redo the experiment all by yourself with no other help except your own lab write-up? In particular, there's a couple of pieces, the theory, but a couple of pieces of equipment that you'll need to use all by yourself. Could you do it all by yourself if this was your laboratory final exam? So don't be one of those people who sits there and just waits for the data, writes it down, and goes home. But make sure you're involved in everything. In particular, I'm going to show you something called a linear measure microscope, which you may or may not have used. Very critical piece of information in this lab. And could you do it on your own, by yourself? So if you're not immediately involved in making the measurements, are you looking over people's shoulders? And then when they're done making the measurement, you check it yourself just to see that you agree with it. Could you do it on your own? Keep that in mind the whole time. Okay, let's show Young's experiment. First off, I have simply a laser. That makes it a lot easier for us. Young had a problem. He needed monochromatic, coherent electromagnetic radiation. That's not as easy to produce if you don't have lasers. We've got the lasers. We've got it invented. So there's a red laser dot on the board over there. And it is exactly one wavelength. It's not a mixture of any colors at all. That is one particular wavelength. It's red. Do you note the granular appearance? It's pretty obvious as soon as you look at it and move your head just slightly, you can see the granular appearance shifting in that little red dot. That's an interesting observation that we will talk about later. Next thing I have is simply this black card, which has a series of different kinds of slits. The way I'm looking at it here, there are different width single slits on one side. There's multiple slits in the middle, and then there's a double slit pattern on this side. As I look at it, it's on my right-hand side. There's a set of double slits. And the double slits on the bottom are very, very close together, and as I move up, the slits get wider and wider. This is the set of slits we're going to use to do today's experiment. We're going to choose one of these sets of slits. And sort of as an experimental procedure, it's going to be important which set of slits you choose, because you need a balance between an image that we're going to see on the board down there and a set of slits which is easy to measure. The broader the slits, the easier they are to measure, but the more washed out the image is going to be. The more fine the image is, the closer together the slits are, the more difficult it is to actually measure the slits. So you're looking for a balance between just wide enough to give you something you can measure here and still gives you a reasonable image down there. Without too much more talk about it, let me just see if I can get the image with just these lights on. Let me turn these lights off, put this up here, and see. Aha. I can see it pretty good. There is a set of dots. Can you see them? Obviously, the light is spreading. There is the single dot without the slits in place, and you can see the size and the limit, and there's no other dots on the image there. When I put this back up here like this, if I can find it, there it is. It definitely spreads the light out. We're getting some kind of interference pattern. That alone, ladies and gentlemen, is enough to verify Young's claim that light is away. That alone, just seeing that image spread, go from a very small point to a broader image like that, that's enough. But yet, we're going to go a little bit further. We're going to try to see if we can learn more and more about the wavelength of light by measuring some of the details. So, having done that, now let me put my fingers in just the right place. I want to darken the room and see if we can see even more dots. So, it takes a few seconds for your eyes to completely darken down. By the way, does anybody know how long it takes actually for human eyes to completely darken down?
Oh, I need
30 minutes.
30 minutes, yeah. Wow. It takes just a minute or so to get most of the dark adaptation, but it takes 30 minutes for your eyes to become totally darkened out. Now let's see, do I get it here? There it is. Now you can see there's a much bigger range there. Can you see? If you can't, I'm going to try to hold it in place and get up from your seat and go take a look. I'm moving. There it is. Everybody can see it? Okay. Oh, excuse me. Lights are back on again. Let's talk a little bit about what's going on, what measurements we're going to make, and how we might estimate the wavelength of light from that image. So we have laser light. Here's the correct. We have laser light illuminating a black opaque surface, allowing light rays to pass just through these two slits. They're continuing across the room to that board back there. I'll represent it like this. And before we started, of course, there was a bright central image right here, right at the center. And what we noticed was there was a series of bright and dark spots. Let's imagine that this spot right here, I'll put it in black just so I can differentiate it here. This is one of the bright spots, which is actually being illuminated with light from these two slits like this. So clearly we are getting constructive interference. When the light waves arrive at this point, they add together to make a bright spot. Otherwise it would be dark. The way of analyzing this is really kind of interesting. If you make out of this image an isosceles triangle, let me check and make sure I use my terminology correctly. Isosceles is two sides equal, right? Okay, good. Equilateral is all three. Okay, so make an isosceles triangle by dropping that line right there. Then this little part of the image right here, this little part of the image, is the path length difference. The path length difference between these two paths to get to that bright spot, just call it bright spot B perhaps. To get to point B, this one simply travels that much further than that one. That's the path length difference. So all we really have to do is to describe that. Well, I see a very interesting way of doing that. I still need yet another color. If I imagine this triangle, look, from here to the bright central maximum, from here to spot B, and this vertical distance here, I will simply call that, oh, I don't know, distance Y. The distance between the bright central maximum and the particular bright spot that we're looking at. I'll call that Y. Call this large distance from the double slit over to the screen, call that capital D like this. And perhaps, I don't know, call this one H, the hypotenuse. H like that. So I've got this triangle, which is of course described by this particular angle, call it theta. Theta is also described here in this angle right here. Calling this distance from here to here, little d, the distance between the slits. Calling this distance d sine theta. That becomes the optical path length difference as we measure this path length with that, compare that path length. And if you don't believe that this is theta, then what I would ask you to do is to imagine, no, I don't have too large objects, but you can imagine as I close this angle, as I allow this angle theta here to close down to 0, of course that's going to close down to 0 also. Or rather, if I generate angle theta here, that's going to simultaneously generate angle theta right in here. So this angle is the same as that angle. The optical path length difference is simply d sine theta. That describes the path length difference. Okay, well that's nice. However, if you stop and think about the image you just looked at, trying to measure the angle, if I was to imagine the line right now being drawn by the laser. So I imagine that line right now being drawn by the laser, and then I imagine the line to the first bright spot. How are we going to measure that angle theta? Not easy, you're right. It's not going to be easy at all. However, we can do some very nice geometry because we can say then, looking at this angle theta, we can say that sine of theta is equal to y over d squared plus y squared. There's the sine of theta. Right? All we have to do is measure d, measure y, and sine is the opposite divided by the hypotenuse. We've got the sine of theta. Beautiful, because now instead of d sine theta, we can write d y over d squared plus y squared. Now we do have something we can measure. I can measure the big D. I can measure the y. Be a little bit of a trick to measure a little d, but I'll show you how to do that in just a minute. So now we've got an expression to describe the optical path length difference, but wait a minute, what we have is constructive interference. Would you agree with me that as long as this is some integral number of wavelengths, you're going to get constructive interference? If this path length is exactly one wavelength longer than this path length, when the two waves arrive at this point, they will interfere constructively. They will add together. Yes. So all I'm saying, that's just what I'm going to say. I'm going to say it in an equation, but I'm going to say that d sine theta equals m lambda, where m could equal, well, could it equal 0? Yes, it can. The bright central maximum is when m equals 0. It can equal 1, 2, and so on, theoretically forever, not really, because the speed of light is not infinite. But we now have, for each bright spot, the bright central maximum is when m equals 0, and for the first bright spot on either side, we have m equals 1, and so on. So finally, we have that theta, lambda, is equal to d sine theta over m, which of course is d squared plus y squared, all divided by m. And our last trick is how to measure d, the slit separation. This is something called the linear measure microscope. Okay, I'll go get the microscope in just a second. But before I do, when you look at the linear measure microscope, you're going to see a double set of slits like this. And d is the separation distance. Of course, you're tempted to say, what is the separation distance? Where would I measure? From where to where would you suppose that the separation distance should be measured? Probably center to center, huh? But look, I'm going to put this in green, I'm going to go like this, I'm going to say D, question mark. It could be there's a D minimum, which I would call this, D min, and a maximum, which I'll call this, D max. And then this, which I will call D average. And how do we know which one to use? Well, you don't. You're an experimentalist. You don't know which one to use. What you do is you say, I will start my calculation by using D average, but I'm also going to calculate the wavelength. This is the minimum little d that could possibly be. This is the maximum little d could possibly be. So that's going to define the range on your answer. Your answer is actually the range between these two calculations, and your best guess is this. But that's not your answer. This range is your answer. Okay, so what I'm going to ask you guys to do is I'm going to ask you guys as a group to start making these measurements. So we're going to darken the room and try to keep it dark for the rest of the hour so that your eyes will darken that nicely. One thing that I would like to have is permanent raw data, which means either we're going to make marks on the board and leave them there forever. Can't do that, can we? Or perhaps we ought to put up a piece of paper, a nice long piece of paper on the board there that you can make the marks. So we'll set this thing all up. You will choose one set of slits. By the way, just so you don't forget, once you've chosen a set of slits that you're going to use, let's use some tape and tape off all the others so that the others cannot be used. There's a whole bunch of slits, and you want to make sure, okay, we're going to use the ones in the middle here, on this side. Once you've decided that, we'll just use tape to block off all the others, and that way you know which set of slits you use. So you'll choose a set of slits, put up a piece of paper down there, and then somebody should be marking each data point. Not the center of each dot, but the size of each dot. Somebody should be down there with a nice pencil actually circling each dot that you see, indicating, of course, the bright central maximum so that measurements can be made from there. And then with that data and the linear measure microscope data, you should be able to determine the ballpark estimate of the wavelength of red light. Yeah?
So should we perfectly square up the laser?
Probably should square up the laser as best you can, but when something is this big, you know, this kind of eyeball estimate is good enough, I think. So yeah. As you're taking the data, put it on the board. Everybody should get a chance to look at least what's going on and gather the data, and this will be a lab write-up. Not due today because we've only got 2 hours today. It'll be due next time we get together is Monday next week, right? What's that date, by the way? I have no idea.
The 24th?
Still February, isn't it? That's the 24th? Okay, I'll find it.
29.
29?
That's what I say. It's like the
The
24th.
32nd of February? Anyway, next Monday.
It is the
Okay, so those of you that came in close to the hour, did you pick up a quiz? Let me restate what I said. earlier today, instead of actually doing the quiz, I'm going to ask you to do the quiz at home. I have here a quiz and a solution. Put the solution underneath. Sometime between now and next Monday, take this as though it were a quiz and then grade yourself. Everybody's going to get full credit on this quiz, don't worry. But what I'd like to do is to try to do this thing as it were a quiz. I would expect that it would take at most 15 minutes to do this thing. And about 13 minutes of that time is thinking about it, and 2 minutes is actually doing it. So that's all the time it should take. You should be able to do it. If not, you've got the solution there. And so this was my way of not wasting time so we can get right to this experiment.
So are we going to have a lecture on this chapter?
It's going to come next week, and things are going to be, we're not going to be real rigid about this is the topics from this chapter and
No,
those are the
my
topics
point
from
is,
that.
can we have this due after the lecture so we have a clue what's actually going on when we try to write it up?
Sure. Sure, you can turn it anytime you want on Monday.
Thanks,
Yeah.
that's so helpful.
You can do it, turn it in, you're gonna get full credit on it no matter what. Make yourself a copy and take it home, you can do anything else. You're gonna get full credit. I see your name on the paper, get credit for it.
That's
I'm gonna
what I'd like to understand what we're doing.
Yeah, so that's why I say you can make copies of it if you want, and do it again later, or do it after you feel like you. But it's pretty straightforward. In fact, it is certainly based only on things that we lectured about last week. Yes?
Is the homework due next Monday?
Yeah,
Okay.
yeah. Okay, let's take about 5 minutes while you folks get ready to make your measurements, and I'm going to go get the linear measure microscope.